charged you to soon.
All right, so we are going to talk about exponential growth and decay functions today, which is an introduction then to logarithms that we're going to start doing. Okay? So get out your graphing calculators. You'll need them because we're going to graph these exponential growth and decay functions, and we're going to use our calculator to do it. Okay? So exponential growth, an exponential function has the form y equals a times b to the x power, where a is not equal to 0, and the base b is a positive real number other than 1. All right? So a is going to be positive, and b is going to be bigger than 1, because if we put 1 in there for b, what's 1 to any power? The same, right? 1. So it wouldn't change, okay? When y equals ab to the x is an exponential growth function, b is called the growth factor. The simplest type of exponential growth has the form y equals b to the x power. So that's the simplest type, because a would be 1 there. I think I wouldn't put a 1 in there, all right? So for exponential growth, that base, thank you, will be, Scott, put the phone away. Oh. And you're playing a game, you can toggle back and forth, right? Oh, okay. So it's growth when the b is greater than 1, okay? It's a growth function when the b is greater than 1, all right? And there's the graph of an exponential growth function, okay? They all look like that. They start out kind of flat, and then all of a sudden they take off, okay? This graph never touches the x-axis. That's called an asymptote. A line that your graph approaches but never actually intersects with, and never actually touches, is called an asymptote, okay? So the domain, your possible x values could be anything, all real numbers, from negative infinity to positive infinity. But your range is always going to be a number greater than 0, because it never hits y equals 0. It gets really, really close to that x-axis, but it never actually hits it. Okay? They all look like that, the growth ones. Just a little bit different version. They might go flat a little longer, then take off. They might go flat a little shorter, then take off. Okay? But the growth ones start kind of flat on the left, and then they start going up really quick. All right? Decay is when the b value is between 0 and 1, like 2/3 or 3/4 or 0.5. Okay? If your b value is between 0 and 1, Varner, it's going to be a decay function, okay? And the decay function, the graph, is symmetric about the y-axis there, like reflects across the y-axis. All right, so they go down real quick, and then they kind of flatten out, the decay functions. It falls, and then again, from negative infinity to positive infinity, all real numbers would be our domain. Any x value would work. But our range is, again, going to be from y up. So y is greater than 0. It'll get closer and closer to that x-axis. But the x-axis, the y equals 0 line, is our asymptote for those. And sometimes they'll move up and down. But for this parent function, That's what it looks like. So those all look pretty much the same too. Oh, good morning, Maddie.
Good morning, Mr. President.
So who's the star or whatever this is?
You guess.
I can't. I looked in Mrs. Gunther's room and you weren't in here.
Yes, it was.
When I looked in there, I didn't see you.
When?
Before class started, I was looking for you because you weren't in here.
I was by the I was on the bench. The bench, you know what I mean?
I don't know what you mean.
Okay.
Well, I'm glad you're here now. Okay. Where's your name? There you go. Madeline Rose. All right, so that's what decay function looks like. All right, so what's my B value? 2. Is that bigger than 1? So is it growth or decay? Growth. Scott, quit playing your game. Yes, you are. Again, because the B value, this, is bigger than 1, it's growth, all right? So punch that in your calculator. Hit your y equals button. 2 caret x. And hit graph. Okay? Looks like what we had already said, right? If you want a table of values, wow, I don't want to start there. I want to start at, let's start at -2 and go by ones. There we go. Let's go up 1 to -3. Okay. So there's a table of values for you as well. As you can see, if I keep going up on my table there, these numbers will just get smaller and smaller and smaller, but it'll never hit 0. Those y values, okay? As I go in the negative direction, I go up in the table, okay? This thing, you can't really see it anymore, but it just keeps going. It just never touches that. It gets really, really close, but it will never touch it. Okay. Again, our domain would be all real numbers. Our range would be all y values greater than 0. Okay. B, what's the second example? What's my base? What's that base? 1/2. Is that between 0 and 1? Yes, so it's decay. Yes, comment.
The last one was the range.
Y is greater than 0. You're welcome. So again, this was growth because the B, the base, was bigger than 1. This one's decay because 1/2 is between 0 and 1. Okay? So to graph it, again, just put it in your calculator, hit your y equals button, and change 2 to 1/2, or you could hit 0.5 if you want. I'll just do it like it shows, all right, to the x power. And we graph it. It goes down quick, and then it flattens out. Just like we said. Okay? So these are really easy to graph because you're going to use your calculator. Our table of values, as I would go in the negative direction, they'd get really big. As I go in the positive direction, they get really, really close to 0, but they never actually hit 0. Okay? This, again, would keep going. Oops. Would keep going, but never actually hit. So again, my domain is all real numbers. Any X value will work. My range is also the same as the decay or the growth one. It never hits 0, so it's all Y values greater than 0. Okay? So if you have to graph something, just use your calculator. That's easy. Again, decay is when the B value is between 0 and 1. Okay, so any decimal less than 1, but bigger than 0, so no negatives. All right? And any fractions or decimals less than 1 and greater than 0. Then it's decay. All right, so exponential models. Some real life quantities increase or decrease by a fixed percent each year or some other time period. The amount y of such a quantity after t years can be modeled by one of these equations. So there's your exponential growth model. Y equals a, which is the initial amount you start with, times the quantity 1 plus r when it's growth. R is the percent of increase. It's a rate. All right, it's in percent, but when you put it in the calculator or in the formula, how do you change the percent to a decimal? There's my little examples. Here they are. What do we do to change a percent? Like, let's say 25% to a decimal. What is that? Baluch, what'd you say? Oh, was it you, Alan?
Yeah, 0.25.
Thank you. All right, so if you have 25%, you're going to change it for R as 0.25. You're going to move that decimal point 2 places to the left. What about 5%? What's that as a decimal? 0.05. Good. What about 1.5%? 0.015. We good on that? We're going to move that decimal point 2 places to the left when we substitute in for this R here. Okay, because that rate is going to be in a percent. Okay? So 1 plus R is the growth factor and 1 minus R is the decay factor. Okay? T represents our time period. Usually it's years, but sometimes it'll change to months or days, depending on what we're doing. Maybe even hours or minutes. Okay? So we're going to use these formulas to help us do some problems. Okay? So let's look at some examples that use that. Right? The value of a car Y in thousands of dollars can be approximated by this model. Y equals 25, the initial amount, but that's 25 what? So the initial price of this car was $25,000 is what they're saying. You understand? Can be approximated by the model 25 times 0.85 to the t power, where t is the number of years since the car was purchased. So when you buy a car, and after you have it a few years, is it worth more money or less money? Less. So is this growth or decay? This is decay, right? And look at this number. Is that number less than 1 or bigger than 1? Less than 1. So by that, we know it's decay, right? Identify the annual percentage increase or decrease in the value of the car. All right? So since it's decay, it's this formula. Y equals A, 1 minus R to the t power. So my 1 minus R equals 0.85. So what do I do to solve for R? What do I got to do? What's the first step to get R by itself? No. Yeah, we want to get this 1 over here, right? We want to subtract 1. So I get negative R equals, what's 0.85 minus 1? Negative 0.15? So what do I got to do to get what R is? Divide by -1, don't I? You guys with me? You guys awake today? So what's the annual percent? What percent is that? 15%. Thank you. And it's a decrease, right? Oops, forgot my E. It says, part C now, when will the value of the car be $8,000? Okay, so here's our problem. And then we turned it into 1 minus 0.15 t, right? You with me? So where do I put the 8,000 to solve this? In for y, right? Okay. So 1 minus 0.85 or 0.15 we knew already was 0.85, right? Since that's a t there, if I'm trying to solve this, I got to divide by 25 first because that's an exponent, the t, right? So what's 8,000? How many quarters go into 8,000? A lot, huh? 320. So how do we solve that equation? Have we learned that yet? We haven't learned that yet. That's where we're going to be headed when we talk about logarithms, okay? So here's what we're going to do instead to solve this. We're going to go to our calculator, and we're going to put it in our y equals, all right? And we're going to use the y equals 25 times 0.85 t, but we don't have a t, so we're going to use x, okay? So that's what we're going to put in our calculator. So 25, parentheses, 0.85, parentheses, caret, x. And we want to find out when it equals what? 8,000. So I'm going to put a y equals 8,000 also. Okay. Now, when I graph this, I will not be able to see the 8,000 one. Okay. So I have to change my window. All right. So I'm just going to hit graph right now. And we'll see the exponential one. Maybe, maybe not. There it is. It's going down. All right. We just see a little bit of it. Okay. But remember, this is only, my window only goes from -10 to 10, right? Well, we're going to start at 0. Okay. And go up to, what was the original price of this car? 25,000, right? So I guess we don't need 25,000 because X is our number of years, right? So we're gonna, that's our Y values of 25. The X, let's just go, that's fine, 0 to 10 years. We'll go by ones there. The Y min would be $0, and the Y max would be 25,000. And let's go by thousands so we can look at it a little better. We don't have to go by ones. And then hit graph, and then we'll be able to see it better. There's our 8,000. Why didn't our other one show up? What did I do wrong? X, 0 years to 10 years. Going by ones. And then 0 to 25. I don't know why it didn't show up. It should have. It's in there, right? The 8,000 is a straight line. Why don't I see the thing coming down? I don't know why I can't see it. Did yours show up? Both of them? Did you use the same window I did?
No, really, I just zoomed mine out a lot.
You just hit zoom out. All right, let me do this. Let me do zoom fit. I think that's 0. Zoom 0 is what I hit for zoom fit. There's the 8,000. I don't know why the other one's not showing up. 25 times 0.85 to the x power, right? Oh, you know why? Since it's in thousands, I should just have put 8 maybe. Let's go to 25,000. Let me see if that works. Just maybe that's my problem. So 25,000 and then 0.85 to the x. There's it is. Okay. So I'm looking for this intersection here. That's our $8,000. And then this is our function decay coming down from 25,000. All right, so we want to find whatever this number is here. That's how many years, right? Our x value. So you can find intersection like this. Hit second trace for calculate, and number 5 is intersection. You trying there on your calculators? Second trace, number 5 for intersection. So I'm going to hit 5. All right, first curve, just hit enter. Second curve, just hit enter. And then guess, hit enter. And the intersection is 7.01 years. And that's 8,000. So that's the point. So it's going to take 7 years for it to drop, or, you know, it's going to be worth, if you want to sell it 7 years later, you probably get 7,000 for it, is what we're saying. Okay. So I think the easiest thing is, instead of trying to figure out like I did what the window was, hitting window and trying to figure it out, all right, just hit zoom 0. You hit zoom and go down to 0, and you can just hit the 0, but 0 means fit, right? Zoom fit kind of fits them both, so you can see both of them, right? All right, so 7 years would be the answer to that problem. All right, here's another one. You guys try this one. This is a boat. Again, it's in thousands of dollars, so that 31 is for 31,000 is what it costs, all right? And I don't think you need to worry about when you hit zoom 0, changing it from 31 to 31,000. All right, so figure out if this is growth or decay, and then figure out the percent increase or decrease. Okay, so write that little equation on your paper so I can give you part C, what you're supposed to figure out, how many years it's going to be worth a certain amount of money, like we just did. So I guess you guys could all tell me, is this growth or decay? Decay, good. What's the percent decrease? 8%, right? It's 1 minus 0.92, right? Which is 8%. All right, so when will it be $9,600? So that's 9.6. Yeah. Well, now you do. Yes, sir. 31. Here, I'll write the equation right here, buddy. So it was y equals 31.92 to the t, right? So what you can do, if you leave it at 31, that's what I should have done on the other one. You leave that at 31, then leave 9,600 as 9.6 on your second equation, and then see where they meet. Didn't show it. I hit zoom 0 for this one now. It should work now. It still doesn't. Why? Hit zoom out then once, see what happens. All right, now I can do it. All right, so I hit zoom 0, and I couldn't see where the two met. So I hit zoom out after that. And now I'm going to go hit second trace, number 5, and just hit enter 3 times. So 14 years. Is that what you guys got? So that's the number of years it takes for that boat. Started out as $31,000 to be worth $9,600, because as soon as you take it in the water once, it loses its value. As soon as you take a car out of the showroom or wherever you got it, the lot, it loses its value. All right, so that's exponential decay problems, those two. All right. Here's one, world population. It's increasing, so that's exponential growth, right? So now this is in billions, okay? So we're going to use since it's increasing, the initial amount, 1 plus r to the t power. We're going to use that one, right? So we're going to write y equals 7.38 is what we started at. That's the initial amount. And then 1 plus an increase of 1.09, which is 0.0109, right? And what's t for this problem? During the next 5 years. So we're just going to put a 5 here. Okay? T years after 2015, which would be right. So this is to the t power for t years. 2015 to 2020 is 5 years, so that's why it was 5. So you just put that in your calculator, and you get your answer, which would be 7.79. And remember, that's billion. All right, so just, again, you don't have to do the y equals. You can just put all that in. 7.38 parentheses 1 plus, remember, you're changing the percent to a decimal, 0.0109. To move it 2 places to the left, close it up. Caret, remember, because you're raising it to an exponent, to a power, 5. And that's where we get to 7.79, okay?
So wait, why could we just put in the calculators? Because like
we have how many years this time?
Okay.
The other one was we were looking for the number of years, so then we had to do the 2 graphs and see where they met. Now, in a week, we'll be able to solve that equation without using the calculator, but we haven't learned about logarithms yet. So you guys try this one. In 2010, the population of a city was about 1.04 million. During the next 10 years, the population increased by about 2.05%. Write an exponential model that represents the population in millions T years after 2010, then estimate the population for 2018. Remember, here's our basic formula. So you're just substituting into the formula. So it's pretty easy. So what's my A value? Alexa, what do I put in for A? Thank you. That's the initial amount. Skylar, what do I put in for R? Right, so we're going to move that to the left too, so 0.0205. And then we would say to the T power, but since it was 2010 and we're looking for 2018, what's my T again?
X.
Yeah, but what number are we going to put in place?
8.
Yeah, thank you. So that's what we're putting in our calculator. So, Ethan, what'd you get?
I forget.
You forget?
I cleared it on accident.
Oh, accidentally on purpose?
Yeah.
Okay. 1.04 1 plus 0.0205 to the 8th, right? 1.22, that's million, right? So basically it's just plug it into the formula, right? If it was decay, it would have been 1 minus R. Okay? So far, so good? All right. 2 more examples. All right. This one's a little tricky, these 2. The amount Y in grams of for the radioactive isotope chromium-51 remaining after T days is this formula, where A is the initial amount in grams. What percent of the chromium-51 decays each day? All right. Well, we want it to be to the T power, right? So we got to do 0.05 to the 128th power. Not 0.05, sorry. 0.5. So I'm going to figure out what that is first. 0.5 to the, okay, and then 128th, I have to put in parentheses 1 divided by, oops, not another one of those. Like that. So that's 0.9755. Okay. So how much decays each day? All right. It's 1 minus that, right? Is what happens each day. So that's the trick, is you got to take whatever your decay is, your number between 0 and 1, and raise it to the 1 over 28, since that was T over 28. And then 1 minus that answer. So it's basically about 0.0244. So 2.44% is what's happened. Okay? So that's the trick. 0.5 to the 128th, so you can get it to the T power, not the T over 28 power. Questions? So this one's real similar. This is 1 over, or T over 13. So this time I have to do 0.5 to the what? Since it's T over 13. 1/13, yeah. Like that. So then you go back into your calculator, if it'll come up for me, there we go. And do 0.5, again, caret to the 1/13 this time. And then we're going to go 1 minus that, which is 0.05. 0.0519. So that's 5.19% decays each day. All right? If you get a problem like that. I don't know if you'll get one like that. So, just wanted to get through all the examples today. There is no homework today. We have a late start tomorrow. We only get like about a 25-minute class tomorrow. So I'm going to let you work on this homework tomorrow during class, okay? We'll call it classwork. Any questions? All right, thanks.